Hi, this is an introduction on molecular orbital theory. So molecular orbital theory really just takes atomic orbitals and combines them into molecular orbitals that are spread out over the entire molecule. And the way that we say that in the mathematical terms is that we're taking atomic orbitals and we're linearly combining them. So we're adding and subtracting atomic orbitals to make molecular orbitals. And there are some rules that we should know. These linear combinations of atomic orbitals are only allowed under conditions of like symmetry. So the first rule that we need to know is that only atomic orbitals that have like symmetry will combine. Or another way of saying this is that combinations of atomic orbitals are only allowed if the symmetry of each atomic orbital is compatible. Another way of saying that the symmetry of atomic orbitals must be compatible is to say that they have to have similar shapes so that they can combine and overlap. And the second major rule is that in order to combine, atomic orbitals have to be able to overlap, and that means that they have to have similar energy levels. So in order for two or more atomic orbitals to combine, these two things need to be true. Another rule that is useful to keep in mind when you're making molecular orbitals is the bookkeeping rule, and that is that the total number of atomic orbitals that you use to combine to make molecular orbitals gives you the number of molecular orbitals. So the atomic orbitals that you combine has to equal the number of molecular orbitals that you get out in the end. So keeping these things in mind, let's make the molecular orbital diagram for the simplest case, which is a homonuclear diatomic molecule with a hydrogen. So I'm going to draw the molecular orbital diagram for H2. But first, let's explain what we mean from up here and how this applies to hydrogen. So when you take two hydrogen atoms and combine them to make a molecular orbital, what you're doing is you're taking essentially two hydrogen 1s orbitals, so that each of those hydrogen 1s orbitals, this is the nucleus and this is the electron cloud. You combine those to get two H2 molecular orbitals. And notice that I am abbreviating atomic orbital as AO and molecular orbital as MO. So in mathematical terms, if I take two different hydrogen 1s orbitals and combine them, that means I'm taking the wave function of one, and I'm going to call the first one A, and I'm going to combine it in some way with the wave function for hydrogen B. The first thing I'm going to do is subtract. When I subtract one wave function for the other, this gives me a molecular orbital wave function. And in this case, because I'm subtracting, it gives me the antibonding orbital. In a qualitative sense, you've probably seen this as taking the positive wave function and adding it to the negative wave function to give you an antibonding molecular orbital that looks like this. And so hopefully you've seen this before. Another way for me to combine these atomic orbital wave functions is to add them. And if I add them, essentially what I'm doing is taking the positive wave functions in each case and I'm adding them together. That's going to give me a molecular orbital wave function. In this case, it's going to be a bonding molecular orbital, so I'm not going to put the star there. And I'm going to draw electron density between the two nuclei, which I can draw like that. And so this is what I mean by linear combinations of atomic orbitals over here give you the molecular orbitals here. You usually see this in the form of a molecular orbital diagram. And there are many ways to draw molecular orbital diagrams. But in this case, we were going to put the individual atoms on either side. So I would put HA here and HB here So these are my two atoms, and I'm going to put my atomic orbitals above them. For HA, I have a 1s orbital, and for HB, I have a 1s orbital. And they should be of equal energy, and so I'm going to draw them at the same height, because remember, energy is a vertical scale. And each of these hydrogen 1s atoms has 1 electron. Now in the center here, I'm going to draw the molecular orbitals for H2. So H2 molecular orbitals are going to be in the center. Now if I combine the two 1s orbitals in a negative way, or if I subtract one from the other, I'm going to get an antibonding orbital, just like this one. And it would be of higher energy than if I added them and got the bonding orbital here. So I'm going to draw the antibonding orbital, and I'm going to draw lines, dotted lines, to show that my two different atomic orbitals are contributing to this. Now, the picture I drew of this antibonding orbital is here. And remember, this represents basically H bonded to H. Now, the inner nuclear axis I'm drawing here is a horizontal line. When you have an orbital that is symmetric to that axis, and in this case, basically, it means that it's spherical around that axis, that kind of orbital is called a sigma bond, or a sigma antibond in this case. So anytime you see a sigma, it means that the bond is symmetric with respect to that internuclear axis. And in every case you'll see me using from now on in this class, I will use the z-axis as my internuclear axis. So this is usually how we draw our coordinate system, so that the z-axis is collinear with that bond axis. And this is the convention you'll also see in most textbooks. It would be acceptable to change that convention for you, like you could use the x-axis for the internuclear axis, but it often causes confusion comparing your work with the book examples or with my examples. So I recommend that in this class you use Z as your internuclear axis. So we just talked about the antibonding linear combination. Let's do now the bonding, or the addition of these two wave functions. You can see that it would match up with this one, and that's what my wave function would look like, my molecular orbital. And again, if this is the internuclear axis, this orbital is symmetric with that internuclear axis, and so this would be a sigma orbital as well. So we combined two 1s orbitals, and we got two sigma orbitals. One is bonding, and one is antibonding. And then the last thing to do is to fill in the electrons, and you always fill in the lower energy orbitals first. And so in this case, we can see that the two electrons go to the bonding orbital, and this has a bond order of 1. So let's go to an example that's a little bit more complicated. We're still going to use a homonuclear diatomic molecule, but we'll use F2 this time. And I'll switch my color. So now we're going to talk about F2. So in fluorine, now we're not only dealing with s orbitals, but we're also dealing with p orbitals. So of the orbitals in fluorine, we're only going to focus on the valence orbitals, because those are the ones that we really think of as contributing to bonding. And all of those valence orbitals are going to be considered here. So the s orbital, the 2s orbital on fluorine, is going to combine in a really similar way as the hydrogen 1s orbitals were. So I'm not going to draw those right now. But I want to talk about how the p orbitals are going to combine. So if I draw my fluorine molecule like this, and I define the internuclear axis as my z-axis, really doesn't matter which way I define the other two axes, or axes. But I'm going to define the fluorine internuclear axis as a z-axis. And now I'm going to look at the two different px orbitals on the fluorine. So if these are the two nuclei of my fluorine, and this is going to be a bond, the px on the first fluorine would look like this, and the py on the, px on the second fluorine would look like that. And these can combine in an additive or subtractive way. In other words, they can constructively or destructively interfere. So if they constructively interfere, or if you add these wave functions, you will get the bonding molecular orbital that would look like this. And if they destructively interfere, if you subtract their wave functions, you would get the anti-bonding molecular orbital that looks something like this. So that is basically what the molecular orbitals would look like from combining two px orbitals on fluorine. We also have py. And again, now these p orbitals will look almost identical, except they're just on a different axis system. I'm going to draw them like that. If they add or they constructively interfere, we get a molecular orbital that looks like this, kind of like a hot dog bun. And if they destructively interfere, we would get the anti-bonding situation that would look something like this. So bonding, px, bonding and anti-bonding, py, bonding and anti-bonding. And now we have pz to consider, and pz will look a little bit different because the pz orbital is along the internuclear axis. So if I take these two and I combine them in a constructive way, my bonding molecular orbital will look like that, and my anti-bonding molecular orbital will look like that. So there's a node here between the two nuclei, just like there is here and here. So in the last example, we called these molecular orbitals sigma bonds. And in this case, we're going to label these bonds as well. And you probably know from general chemistry that when you combine p orbitals, you get one sigma bond and two pi bonds. And hopefully you can see where this comes from. If it's a sigma bond, then it's going to be symmetric with the z-axis or the internuclear axis. So can you pick out the one here that is symmetric with respect to the z-axis? It turns out that it's these two. Both of these, if this is the z-axis, in both of those cases, the orbitals are symmetric with respect to that z-axis. And so this is your sigma star and your sigma bonding. And the other situation here with the px and py, you can see that these are not symmetric, or they're not spherical or around the z-axis, which is here, 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 and here. And so these are not sigma, they're pi. So here we have a pi bonding, pi anti-bonding, and another pi bonding and pi anti-bonding. In this class, you'll also find that we use another type of subscript to talk about the symmetry of the orbitals. The sigma and pi tell you with their symmetry with respect to the z-axis. And there's another set of subscripts now, u and g, that are going to tell you something about the symmetry of the orbitals with respect to an inversion center. Or another way to say an inversion center is basically just the center of the system. So I'm going to draw the center of each system here, the little pink dot. So U stands for ungerade, and G stands for gerade. And these are just two German words that mean uneven or even. So if it's even with respect to the inversion center, it will be given a G subscript. And if it's uneven with respect to an inversion center, it'll be given a U subscript. So let's start with the top. If I start here and go across the inversion center to the opposite side, I would start in a negative lobe and end up in a negative lobe. if I started up here and went down here through the inversion center, I would end up, or I start in a positive lobe and end up in a positive lobe. So this is basically when you go through the inversion center to the other side, you end up in a place that looks the same. That means that this is even with respect to an inversion center. So this is a pi star G orbital. In this case, you go from one side through the inversion center to the other side. No matter how you do that, you will end up on the opposite lobe than where you started. So if you start in a positive lobe up here and go through the inversion center, you'll end up on a negative lobe. And so this is uneven, or U. You'll find that the pi star are going to be all G, and the pi bonding are going to be all U, or ungrade. With the sigma, we actually have the opposite. When you have a sigma bonding, if you start here, you end up here. This is basically the same kind of place. And so the sigma bonding is G, and the sigma star is a U. Okay, so now let's draw the molecular orbital diagram for fluorine. Again, a homonuclear diatomic molecule. So I'm going to only focus on the valence orbitals. My 2s is going to be the same energy level as my other 2s. And then I have 3 different 2p orbitals that are going to be equal energy level. And I'm going to use a different color to show my F2 molecular orbitals in the middle. So the s orbitals will combine with each other in a bonding and antibonding fashion, similar to the way that the hydrogen 1s orbitals did. So I'm going to have a bonding sigma, 2s, and an antibonding sigma, 2s. And I can show dotted lines to indicate how these are combining with each other. With the 2p, I will have a sigma 2p bonding and 2 different pi 2p bonding. And then I will have pi 2p antibonding and also a sigma 2p antibonding. Oops, sigma star. And I should label these with my U and G subscripts. And so for my sigma, I said that the bonding was going to be a G for the sigma star, which I didn't label. It's really a U. For the sigma 2p, oh, sorry. You actually don't label those with G or U. You only label these. So G bonding, sigma is G, bonding pi is U, antibonding pi is G, and antibonding sigma is a U. So then we should draw these dotted lines to show that the orbitals are contributing, or the atomic orbitals are contributing to these molecular orbitals. So now you can see how to draw the atomic orbitals, and we can now fill in the electrons. So the fluorine has 7 electrons on each one. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And that means we have 14 total. And hopefully you remember how to calculate bond order. So in this case, these 2 orbitals, the bonding and the antibonding, cancel each other out. There are 2 antibonding full here, 2 bonding get canceled, and so you have a bond order in fluorine or difluoride as 1. And to practice this, I recommend that you try the molecular orbital diagram for O2. For this, you should get a bond order of 2. And you should also find that this molecule is diamagnetic. So So please try to draw the molecular orbital diagram for O2 and make sure that you come up with these things so that you know that you're doing this correctly. In the next video, we're going to talk about a little bit more complicated case where we're using two different atoms, so not just two fluorines, but a hydrogen and a fluoride, for example, in a heteronuclear diatomic molecule. And then we'll move on to larger polyatomic molecules. So I'll see you then.